everyone. I'm Svetlana Sakova, developer advocate at JetBrains. Today we're discussing the Kotlin solution for one of the advent of code puzzles, binary boarding. You can find the task description at adventofcode.com 2020 day 5. Note that the puzzles for different days are totally independent of each other, so you don't need to check the previous ones to see how we solved this one. I hope you learned something new. We are boarding the plane. We need to analyze the list of boarding passes and in part 1, find the seat with the highest seat ID. In part 2, we need to find the only one missing seat from the list, which is ours. There are 128 rows on the plane and 8 seats in each row. A seat then is represented as a row number and a column number. The row is encoded as a combination of 7 Fs and Bs, where F means front and B means back. The column is a combination of 3 Ls and Rs, where L means left and R means right. The encoding works as follows. First, let's see how to find the row number. We start by considering the whole range, rows 0 through 127. The first F means to take the front part, or the lower half of the range, keeping rows 0 through 63. At this point, we exclude half of the rows and know that our row can only be in this range. The second B means to take the back part, or the upper half of the remaining range, keeping rows from 32 to 63. The next F means to take the lower half, keeping rows 32 through 47. We continue this process, and the final F produces the answer. It keeps the lower row of the 2 remaining ones, and the resulting row is 44. A similar procedure works for finding a seat in a row. We start by considering the range from 0 to 7. The first R means to take the right part, or the upper half, keeping columns 4 through 7. The second L means to take the left part, or lower half, keeping columns 4 through 5. And the final R chooses the upper of the 2, column 5. Every seat has a unique seat ID. It's calculated by multiplying the row by 8, then adding the column. The puzzle input is the list of the boarding passes. The first task is to find the boarding pass in this list with the highest seat ID. As usual, it works best if you first solve the task and then check the solution. So if you want to do it, press pause here, and right afterward, we are discussing the solution in Kotlin. Let's first discuss the encoding of the boarding passes. For those who haven't immediately recognized it, it's a nicely hidden binary representation of natural numbers. Let's take a closer look. First, let's discuss how we find the row number. There are 128 rows on the plane, which are encoded with 7 bits. These bits are called F and B in the puzzle, but have the same meaning as 0 and 1 in the binary representation. What's described as a way to find the exact row of the boarding pass may remind us of the algorithm used to convert a binary representation of a number to a decimal. Let's consider our example. F is equivalent to 0, B to 1. We can rewrite the encoding then as a binary representation of a number. Each bit in a binary representation has an index and corresponds to the power of 2. We remember that F means to take the front or the lower half, while B the back or the upper half on each iteration. Taking the lower half is equivalent to not adding the corresponding power of 2 to the result, or multiplying it by 0, while taking the upper half is equivalent to adding it to the result, or multiplying it by 1. The maximum value that can be encoded via 7 bits is 71 bits, or 127 in decimal form. That's when we take all the power of 2 terms to the resulting sum. Each bit is responsible for taking or not taking its part of the range. If it's 1, we add the corresponding power of 2 to the result. If it's 0, we skip it. Let's discuss the correspondence to the front-back encoding. We start by considering the whole range from 0 to 127. The first f means to take the lower half. That's the same as not adding 64 to the result. That keeps the result in the range from 0 to 63. The second b means to take the upper half. That's the same as adding 32 to the result, keeping rows from 32 to 63. The next f means to take the lower half or not adding 16 to the result, keeping rows from 32 to 47, and so on. We take 8 and 4 as their bits are 1s and discard 2 and 1 as their bits are 0s. And we have the resulting sum 44. Decoding the column follows the same logic, but now R takes the upper half and corresponds to bit 1, while L takes the lower half and corresponds to bit 0. For our example, it's adding 4 and 1 to the result, producing the column number 5. The last part is converting the row and the column numbers to the seed ID by following the formula. Multiply the row by 8, then add the column. But if we look closer at this formula, we'll notice that we don't need to find the row and column separately. We can simply add all the row bits with indexes increased by 3 to the result. Note that 8 is a power 3 of 2. This bit operation is formally called left shift. A little bit of math and the Kotlin solution is almost one line. Let's now implement that in Kotlin. We need to replace front, back, and left, right with 0, 1 notation and converge the resulting binary representation to an integer. Each of these operations is one function call. The string replace function replaces all occurrences of the old character with a new character. There are two more similar functions. If you need to replace each substring with a new string, pass strings as arguments. To replace each substring that matches the given regular expression, use another function, taking regex as an argument. The string toInt function parses the string receiver as an integer in the specified number base, or radix. In our case, we specify that the radix is 2, so it parses the binary representation of the number. There is no need to re-implement the conversion algorithm from scratch when you can use the library functions. Unless you specifically want to practice, of course, but that's not the goal of this puzzle. That's it! We go to the seed ID from the boarding pass and can continue with the task. Let's now solve part 1 and find the maximum seed ID. As usual, we need to read the input first. After implementing the conversion function, it's quite straightforward. We read lines from the file and convert each line to the seed ID. The seed IDs list is a list of integers, and the only thing left is finding the maximum in this list. There is no need to implement it from scratch. We can simply use the max in our library function. We found the seed with the maximum seed ID. The second part of the task is finding the vacant seed, which is missing from the list. There is only one. However, the task description specifies that some of the seeds at the very front and back of the plane don't exist on this aircraft, so they are missing as well. This way, we can simply iterate through the range from 1 to max ID and check for missing seeds. we'll also find those at the very front and back. Our required vacant seat is not on the edge, which means it's the only missing seat that has both its neighbors present on the list. We can check exactly this quality, that the seat itself is missing, in other words, not occupied, but both its neighbors are occupied. To make our code more expressive, let's add a function checking whether a given seat is occupied. It checks that the given seat index belongs to the list of seat IDs. To make this check fast, we convert the given list to a set. Kotlin allows us to create local functions, in other words, functions inside other functions. That's really convenient for such short and simple cases. The isOccupied function captures the outer variable, occupied seats set, and we don't need to pass this set explicitly as a parameter. Now the only thing left is finding the desired seat index. When the seat is not occupied, but the neighboring seats with indexes -1 and +1 are both occupied. We call the find function on a range from 1 to max ID and perform the check for each index in this range. And that's all. The whole main function that solves both parts of the task is pretty concise in the end. Note that in order to use max ID as the range upper bound, we call two exclamation marks, since the max or null function returns a nullable value. Specifically, it returns null if the list is empty. Following the Kotlin philosophy, you would expect to find the max counterpart throwing an exception if the list is empty. And you're right! However, in version 1.5, the max function is deprecated and will be totally removed and replaced with the function throwing an exception in the future versions. The max function was present in the standard library from Kotlin 1.0, but returned a nullable value, and now the Kotlin team is slowly fixing this small discrepancy. Until the max function appears in the standard library, it's fine to write max and null with a not null assertion operator to explicitly highlight that you need the non-null value as a result, and you prefer an exception if the list is empty. Alternatively, to avoid having exclamation marks in the code, you can use max of it until the max function reappears in the library. That's it! We discussed how to solve this puzzle. We recognized the binary encoding for the numbers, discussed a bit how it works, and saw the solution in Kotlin, which is quite simple thanks to the Kotlin standard library functions. I hope you enjoyed the video. Don't miss the solutions for other Advent of Code puzzles. Thank you!